Hello, I would like to welcome you to lecture 22 of 3N03. We'll discuss in this lecture some of the arithmetic circuits, including half others, full others, half subtractors, and full subtractors. And many other arithmetic circuits can be implemented using combinational logic. So the methodology that's explained here can be really applied to circuits that can do simultaneously addition or subtraction, or circuits that can do multiplication and so on. So I'm just giving you a flavor of what can be implemented using combinational logic, but there are so many other arithmetic circuits that we can build using very simple logic gates. Okay, before I proceed to the logic gates, I thought of mentioning a couple of gates we did not discuss before. We discussed the gates like the AND gate, the OR gate. We discussed the logic inverter, we discussed the NAND gate, we discussed the NOR gate. This one here is an XOR, exclusive OR, and this is the symbol that we use for an exclusive OR circuit, and the exclusive OR will give you 1 only if one of the two inputs is logic 1. So you can see here when both of them are logic 1 you get 0, when only one of them is 1 you get 1. So it's an exclusive OR as the name implies. So it removes the one here from the entry of the normal OR gate. The second gate that I would like to mention is the exclusive NOR, and the exclusive NOR will detect that the two inputs are equal. It is the negation or the complement of this exclusive OR, and you can see when you have 0 and 0 you get 1. When you have 1 and 1 you get 1, otherwise you get zeros. So this one can be used to detect that two inputs have the same logical values. And I'm showing exclusive NOR because as I will show you in tutorials, it is very easy to implement NORs, NOR, NANDs, exclusive NOR using complementary MOS logic. And we'll be showing some example on that in the tutorials. Okay. The first circuit we'd like to implement in this tutorial is the half adder, and half adder is simply represents the addition of 2 bits. We know when we add 2 bits, say a bit is 0 and a bit is 0, the result will be equal to 0, and when we have 0 and 1, the result will be equal to 1. When you have 1 and 1, the result will be 0, and then you carry 1. Okay, and then the last one is when you have 0 and 1. 0 and 1 will give you also 1, and then you don't carry anything. So this is the how we add one single individual bit that's isolated from any other bits you may have. So for example, when we have a word can have 16 bits or 32 bits or 64 bits. Here I'm assuming for this table that I'm doing a half adder. I'm assuming that I'm not taking into account any carry that I may have from other bits, other neighboring bits. So here when you add 0 and 0, your output, your sum is 0, and you don't have any carry over or carry out. When you have 0 and 1, your output is 1, you don't have any carry out. When you have 1 and 0, you have 1, and you don't have any carry out. Only when you have 1 and 1, the result is 2, but 2 cannot be represented in a single binary digit, so the result is 0, and then we carry 1 to the next bit. So this is a truth table that try to model this addition operation. If you take a look here, you'll see that the sum will be 1 when A is 0, B is 1, and when A is 1 and B is 0. So the sum can be written as a logical expression as A B bar plus B A bar. For the carryover, you get only carryover if both A and B are 1s. So the carry is simply equal to AB. Okay, so these are the two expressions that we can use to implement the half adder. And half adder simply adds a bit to another bit. It does not take into account any carry in that's coming from another bit. Okay, but when we are building say a 16-bit adder, we have to take all this into account. Okay, this is the implementation of the half adder, and as we agreed that the sum here for this circuit is simply equal to A B bar plus B A bar. It simply gives you 1 only if one of them is 1. only, so it's an exclusive OR circuit, and this is why we represented the sum here by an exclusive OR. While the carry, as we agreed, you get only a carry out or carry over here. C is equal to AB only if both of them are ones. So in that case, this is how we can build a half adder. And as I said, this does not take into account that you have another bit being carried in. So if we were to implement a full adder, we have to implement a function f, which is equal to a plus b plus a carry in, and this carry in is coming from another bit, from a neighboring bit. So let's now take a look at how we can carry, or how we can implement this full adder, and this full adder will allow us to do adding n number of bits together, because you take into account the carry in coming from neighboring bits. Okay, this is the truth table of the full adder. The full adder, as we agreed, is trying to add a plus b plus a carry in. Where would this carry in come from? For example, I can give an example. When you have 1 1 0 1 and you add that to 1 1 0 1 here. Okay, when you add for here 1 plus 1 will give you 0, and then you carry 1. So this is called carry in. Okay, so in the next bit, in order to get the correct answer, you have to add a plus b plus the carry in, and here in this case 1 plus 0 is gonna give you a result of 1. For example, the next bit, you are adding a plus b, there is no carry in, a plus b, this will give you the result will be 0, and you have 1 carry out. This carry out will be carried to the next bit and becomes a carry in to the next bit. Okay, so there is 1 carry in here. When you have 1 plus 1 plus 1, this will give you 1, and you have carry in of 1. Okay, so this is how we would like to implement here. If you take a look at the logic table, the logic table simply implements a plus b plus cn, and this will give you the sum, and if the sum cannot accommodate the result, we carry out 1. 0 plus 0 plus 0 will give us 0, carry out 0. 0 plus 0 plus 1 will give us 1, carry out 0. 0 plus 1 plus 0 will give us 1, carry out 0. 0 plus 1 plus 1, when you have 1 plus 1, this is 2, you cannot accommodate that in a single binary digit, then the result is 0, and then you carry out 1. When you have 1 plus 0 plus 0, the result is 1, you carry out 0. 1 plus 0 plus 1 will give us again 2, so this will be 0, and then we carry out 1. 1 plus 1 plus 0 will give us 0, we carry out 1. 1 plus 1 plus 1, this is the case we had here in this bit, and this will give us 1, sum is 1, and the carry out is 1. So we'd like to be able to implement a combinational logic circuit that implement this logic function. And the way to do this, and for any truth table really, if we want to simplify it, we have to build a corresponding Carnot map, and then we try to see similarities in the table, and then we try to find a more concise expression for the logic function. So for the full adder, we have to build 2 Carnot maps. One is for the sum. So this is a Carnot map for the sum, and this is a Carnot map for the carry out. Okay, remember, a full adder receives 3 inputs, A, B, and Cn, and it creates 2 outputs, C out and the sum. So here we lump A, B together, and then we have the Cn as a separate variable. And as you can see in the Carnot map, we allow only one parameter to change at a time. So going from 0, 0, 0, 1, we go to 1, 1, and then we go come back to 1, 0. The same thing we do it for the other table as well. For this one here, in this table, there isn't really much we can do, because you can see the ones are separate. You cannot put them together into groups. So for this one here, you have A, B are 0, C is 1. So the logical expression for this one is A bar, B bar, Cn. This one here, A is 0, B is 1, and Cn is 0. So this logical expression for this one is A bar, B, Cn bar. The third one, A and B are 1s, and Cn is 1. So the logical expression is A, B, Cn. The last one here is A, B bar, Cn bar. And this is what you have here. These are the four terms that we can get from this Carnot map. The Carnot map for the carry out can be simplified because if we can sum these two together, okay, can put these two together, and you can see in these two, B is always 1 and C is 1, Cn is 1, so the logical expression corresponding to this one is Cnb. Now we can lump these two together as well, we can group them together. Here A and B are 1 regardless of Cn, so the logical expression for this one is AB, which is this one here. The last one is this term here, and this term will give us 1 when A is 1 and Cn is 1 regardless of B. So this expression is simply A Cn, and this is the one that we have here. So by doing that, we are able to simplify the expression for the C out and for the sum. So we can implement, all these can be implemented as sum of products. We can do that. If here we have three input, we can use 3 input AND gate, or as we explained earlier, you can use a cascade of 2 input AND gates. And here, of course, you require 4 input OR gate, or can use 2 cascades of OR gates. This should be fine. For this one, this I have only 2 inputs, so you have 2 input AND gates, and then this is connected to a 3 input OR gate. Okay, so this is the implementation that we have for the for this full adder. A bar, B bar, Cn, you AND them, you take them to the OR. A bar, B, Cn bar, the same thing, A, B bar, Cn bar, and then A, B, Cn, they are ANDed, and then they are OR. This is called sum of products. We've talked about this before. For the C out, we have 3 terms, AB plus BCN plus ACN, and again you AND them and then you OR them at the output. And again, these OR gates can be represented by a number of cascaded OR gates, and these AND gates as well can be represented by a 2-level AND gate. Another circuit of interest to us is the subtraction. How we can do subtraction? We'd like to subtract A minus B, and here we are doing a single bit subtraction. If you want to do multiple bits, you have to include a full subtractor. Full subtractor takes into account that a carry was taken from that bit. So what we are doing right now, we are simply subtracting a bit, which is maybe we're trying to subtract something like 0 minus 0, or 0 or 0 minus 1, or 1 minus 0, or 1 minus 1. This is what we're trying to subtract, and each one of them is a separate operation. Okay, so when you subtract 0 minus 0, the result is 0, the difference is 0, and you don't need any carry. When you subtract 0 minus 1, you cannot do that. Then you have to borrow from the neighboring bit, you have to borrow 1. Okay, so there must be something being borrowed here. Okay, and so this is telling you have to borrow 1. So the result of this one will give you 1, and there is a borrow. Okay, so the borrow is 1, and this is what you see in this entry here, 1 and 1. When you're subtracting 0 minus 1, the difference is 1, and the borrow is 1. When you subtract 1 minus 0, the result is 1, there is no borrow. 1 minus 0, the result is 1, there is no borrow. The last one, you subtract 1 minus 1, the result is 0, and the difference is 0, and you don't need a borrow. Okay, so here, if you take a look at this one here, you can see that the difference is 1 only when A and B are only one of them is 1. So this is an exclusive OR implementation. Okay, so the difference is 1 only when A is 0, B is 1, or when A is 1 and B is 0. So this is why we implement the difference as an exclusive OR. The borrow out appears only in one case, when you have A bar B. So this is why here we take A, we invert it, logically inverted, and then we end it with B. So here we know that our borrow out, this B out here, is simply equal to A bar B. So this is an implementation of a half subtractor. This half subtractor does not take into account that when you are doing subtraction, there was something borrowed from that bit. Yeah, I mean, you're not only carrying A minus B. For example, if I want to subtract 1, 0, 0, 0 minus 0, 0, 1, 1, say. Okay, so 0 minus 1 will not work. Okay, then you have to borrow 1. So this is what we have been doing. We borrowed 1. Okay, we borrowed 1. So the result will be 1 here. Okay, so the result will be 1. and this one here now is not a 0 because you borrowed something from it. So this wasn't taken into account. So what you have to implement for this bit here is really 0 minus 1 minus 1, because you borrowed already 1 to the other bit. So the full subtractor must implement this, that if something was borrowed already from that bit, you have to take it into account subtraction. So the next bit here, what you're going to be, the subtraction you're going to be doing is 0 minus 1 minus 1, because you already borrowed 1 for this other bit. And the same thing will apply to the others. So this is the truth table of the false subtractor, and as I mentioned in the previous slide, this is really implementing A minus B minus this borrow in. You assume that something was subtracted from that bit, and of course this will going to give you the difference, and if you need to borrow out, you take a borrow out from that one. So let's see. So when you subtract 0 minus 0 minus 0, the result is 0, and you don't need a borrow. When you subtract 0 minus 0 minus 1, this means you're subtracting 0 minus 1. 0 minus 1 means you have a result is 1, and you must borrow 1. When you subtract 0 minus 1 minus 0, again, the result is 1, and then you borrow 1. When you subtract 0 minus 1 minus 1, this is the case I mentioned earlier. You have to borrow, of course, 1, and this one will move here to become 2. So 2 minus 1 minus 1, you get a difference of 0. The same thing is happening here. 1 minus 0 will give you 1, there is no borrow. 1 minus 0 minus 1 will give you 0, there is no borrow. 1 minus 1 minus 0 will give you 0, there is no borrow. The last one is 1 minus 1 minus 1. You cannot subtract 2 from 1, then you have to borrow 1. So 1 is here. So this term here becomes 3, really. Effectively it becomes 3. And then you have 3 minus 1 minus 1, you end up with 1. Okay? So this is a logic table. And again, any logic function can be implemented. You simply try to see when the output is 1s or 0s, and then you try to simplify it using Carnot maps to see how you can try to simplify it as much as you can, and then you can implement it using logic gates. So here we'll create 2 Carnot maps. The first one for the difference, the second one is for the borrow out, and then we'll try to see how we can simplify the expression. Okay, so for the Bn, for the first one, the difference here, this is a Carnot map for the difference, which is taken from the truth table. You can see there isn't really much we can do about it. It is already it's fragmented a little bit. We cannot group these ones, but you notice here something that this is an odd parity. Odd parity means that this will give you 1 only if 1 or 3 of the bits A, B, and Bn are 1s. So 0, 0, and 1 will give you 1. If they are all 0s, you get 0s. 0, 1, and 0, you get 1, but 0, 1, and 1, you get 0. So this detecting odd parity. It will give you 1 only if an odd number of these bits A, B, and Bn are 1s. Okay? When 2 of them are 1, as you can see here, 1, 1, and 0, you get 0. But 1, 1, and 1, you get 1. Okay? So this is called an odd parity, and by the way, this can be implemented by 3 input XOR. So if you want to write an expression, logical expression for this one, A bar, B bar, Bn, A bar, B, Bn bar, A, B, Bn, the last one is A, B bar, Bn bar. And these are the 4 terms we have here. For the borrow out term, again, we got this from the truth table. You can do some simplifications. You can simplify these 2 bits, these 2 outputs together, these 2 outputs together, and these 2 outputs together. These 2 here will give us that when A is 0 and when Bn is 1, you get 1. So this is A bar Bn. This is what we have here. And for this one here, you can see that when A is 0 and B is 1, regardless of Bn, you get 1. So this is A bar B. A bar B here, this is this one here. Okay, so this is A bar B, and this one here, as we said, it's A bar Bn. The last one that remains is this one here. This one will give you 1 if B is 1 and Bn is 1. Okay, so this is B, Bn. So this is, we can implement this, of course, as sum of product. There is no problem. This one, as I said earlier, this one here is really an odd parity function. So it's a 3-input XOR. So if you take a look at the available literature, you know that you have an XOR that has 3 inputs. This means that it's an odd parity check. It creates an output only if 2 of them is 1. If an odd number of them is 1. So when you have 1 is 1, when 3 of them are 1s. For all the other inputs, it will create 0. So finally, this is how we can implement this full subtractor. This is a difference, as I said. The difference, as I mentioned, is really a 3-input XOR. It's an odd parity checker. Okay. While for the B out we had 3 terms, and we implemented a sum of products and followed by OR gates. And as I will show you in the tutorials, we can implement really any logic function, whether it's addition, subtraction, multiplication, addition, subtraction, using the same procedure I explained here. You build the truth table, you build the Carnot map, you simplify it, and then you implement it using gates. And as I explained it partially in the tutorials, and we'll continue to do that, all these gates can be implemented using diodes and using transistors. So we can implement them and then build any logic circuit we are interested in.